Ready, shall we get started?
Sure.
Sweet. So I think most of you know by now, but my name is Ada. I'm the TA behind all of the programming assignments. I don't know if that's a good thing or a bad thing. I guess we'll find out. And I noticed that most of you managed to do kernel perceptron successfully in this last homework. But based on questions I got in office hours and on Piazza, it seems like a lot of people are still struggling with the basic insights. And it's not your fault. They were, we went through them quite quickly in class. But what I want to do today is to go back to, not the details of kernel methods, but the absolutely basics to make sure that we understand what they're useful for, why they make sense, and how we use them. Okay? So I want to start with a very simple question. Can anybody tell me in one sentence what kernel methods are useful for? Like, what do we do with them?
When we have inner products and we just apply some kernels, so we do not really need to set the point to higher space with higher dimensions. We just use inner product. That's all.
So all of that is true, but I would argue that you mostly told me how we do it, as opposed to what the core problem that we're trying to solve is.
Complex decision boundaries and fits.
Exactly, complex decision boundaries and fits. To rephrase that, what kernel methods are good for is to learn arbitrarily complex functions. That function might be a discriminant function, in which case you're going to get an arbitrarily complex decision boundary. Or it might be just a prediction function, as in the case of regression and kernelized regression. But the core idea that should be the one-sentence description in your mind is that kernel methods help you learn arbitrarily complex functions. And they don't come out of nowhere. They come from a progression of ideas that we've seen through the entire class. And I want to go through this progression of ideas very, quickly, but just to make sure that we're all on the same page, okay? And I'm going to demonstrate this mostly in the context of classification. But if any time through the revision you're not sure how this applies to regression, just shout regression out there, and I'll do the regression case as well, okay? So in the case of classification, we are given a bunch of data points. Let's assume that the data points are in 2D for now. And the function you're trying to learn is a labeling function. A function that tells you that some of these points are pluses and some of these points are minuses. And this function is going to be a function over the entire domain. And you can imagine that it could look in absolutely any way you want to imagine. So all that it does is it takes regions of the space and calls all of them plus, and regions of the space and calls all of them minus. If we say classification, we haven't yet said any particular form of the labeling or of the discriminant function we're talking about. Now, this is the most general idea we would like to go with when we go with classification, but that's not what we do. That's not how the first algorithms you learned in the first lectures look like. Why is that the case? I warn you that this is going to be interactive. If nobody answers a question, I'm not going to move on. I've got all the time in the world. So why do people think that what we started with is, logistic regression, not something that learns this? Would you know how to start with something that learns this? If you were, first class of machine learning and you were given this classification problem? Exactly. So the reason we didn't start with this is because we don't know how to represent arbitrarily complex functions. We don't know how to represent the classification blob that says that this is plus and this is minus. So through the term, you've seen a progression of ideas that started from very simple classification functions to more and more complex. And the first idea you saw, so the question here is what types of functions are we learning? Is this writing big enough? Can people in the back see? Okay. So what's the first type of function that we learned to classify with? Linear, exactly. So we first saw linear functions. And we saw that even making this very simple assumption, the reason we made this very simple assumption is so that we know how to manipulate this function. We said that for any linear function, we know how to represent it very simply through a vector of weights that's perpendicular to the function. If our linear function is in 3 dimensions, then our vector of weights will be 3-dimensional. So all of this seems really plausible to save in a computer and feed to an optimization algorithm. But we saw that even for this very restrictive assumption, there were lots of different ways to define this problem and to go about solving it. So the question was, even once you've decided that what you're going to learn is a line, we saw at least 4 different ways to learn a line. What did we see? Goodness. Okay. So I heard logistic regression. I heard perceptron somewhere. Naive Bayes. And SVM, exactly. And they all did something very different. Super briefly, not kernel related, but I just want to make sure we all have this in our mind. So starting with logistic regression, what logistic regression did is that it looked at all of the points. It chose a line that is characterized by W. And it looked at all of the points and said, points on one line are minus, points on the other line are plus, on the other side of the line are plus. And furthermore, we're going to calculate a confidence, a probability that they're of the class we predict they are. So if something is very far away, you look at the formulas and you see that if it's very far away from the line, our confidence is high. We expect that it's definitely a minus. And if it's very far away from the line here, we expect it's a plus. But if it's very close to the line, then we're still going to return a minus, but our probability will be more like 0.55. So that's what logistic regression did. Okay? What perceptron did was very, very different. So perceptron started again from something like this. And it started with some random line. And it looked at it, and it found an error. And it said, whoops. I swear that's what our computer says. And when it finds an error, it adjusts a bit its estimate to account for that error. So it goes like, oh, there's a plus on my right where it should be on the left. Let's move a little bit this way. This is my new decision boundary. That's a completely different principle from logistic regression, but it's still fundamentally trying to do the exact same thing, which is learn a discriminant function, which we happen to say should be linear, because that's just how smart we knew how to be. So this is logistic regression, logistic, perceptron. The other thing we learned is SVMs. What do SVMs do? How are they different from the perceptron? Go for it.
They optimize the margin.
What does that mean intuitively?
They try to keep the distance between the data points that are closest to the decision boundary the largest possible.
Exactly. So SVMs noticed, they're very similar to the perceptron in some sense, but they noticed that the perceptron, even if the data set is separable and multiple decision boundaries are possible, not all of them are just as good. So if you have some data points here and some data points here, this is a fine decision boundary, this is a fine decision boundary. Which one's better and why? The vertical one, and it's better because? Exactly. So like intuitively what that means is I have leeway. I have some buffer. My points are far away from me. If the points have a bit of noise, it's fine. So that's the kind of way of thinking that all of these algorithms we see all they're doing is that they're thinking of a clever way to come up with a function that's linear. Okay, so we saw linear functions. Say that our data set is not linearly separable, and there are very simple ways to come up with an idea that's not linearly separable. So the examples that we like a lot, because they're so easy to visualize, is 1D examples. What if you have something like this? No line in 1D, which is just a split, a point, will separate these, obviously, right? So what is the next thing we did? We know that we want to learn, again, a function that discriminates them. So we want to learn something that says this is plus, this is minus, this is plus, this is minus. And we tend to represent that usually by choosing a function taking its sign. So we'd represent it like this. We'd say this is a nice classification function. Whenever it's greater than 0, it's a plus. Whenever it's smaller than 0, it's a minus. So first we said line's not good. What's the next thing that we saw? Polynomials, exactly. And the reason that makes sense, the reason I want you guys to think about this as a progression, is that, again, what we're trying to do is to get flexible functions. But we want to get flexible functions. Was there a question? No, OK. But we want to get flexible functions in a way that we still know how to manage. Polynomials are a great idea because we understand polynomials. We know how to represent them. They're not like what Jeff likes to call infinite information. They're perfectly fine, finite information, because you can represent them, if it's a polynomial of degree n, through n plus 1 parameters. So that's the next idea we saw. We saw it less in classification, because it's not immediately clear why our class would be separated by a polynomial, but we saw it a lot in regression, where you can easily imagine why some data set would be polynomial, right? So our next idea was polynomial. And in general, the generalization of this idea is to use what is called basis functions and do a weighted sum of basis functions. So what that means is in the polynomial, we had sum of ai x to the I. We call the x to the I the powers of x basis functions. There are components, and we combine them to create a polynomial. But if you remember what we saw from class, we saw an example of where we were combining sine functions. We took lots of sine functions of different frequencies, and we took a sum of them to generate a simulation of a process that varies at different periodicities. I think we took the example of the financial market that you expect varies every week and varies every month and varies every year, right? Is this familiar to everybody? Good. OK. So now we can generate something like that. But that's still not like super, super, super general. So when these methods failed, people took data sets and they tried linear and it sucked, and they tried polynomial and basis functions and it didn't do anything. They went back to the idea of trying to capture arbitrary functions. And again, what's difficult about arbitrary functions is that we don't really know how to put in our computer memory an infinite dimensional arbitrary function. So the next idea that people came up with, if you remember from class, is this idea that you can think of as coming from calculus. You know how when you want to integrate something, you like take little chunks of it and you assume it's constant on those chunks. So if you're trying to integrate a function like this, you would just take little chunks and you assume it's constant on those chunks and you'd integrate it like that, right? Are people familiar with? Good. OK. So the exact same idea, we're like, OK, well, why don't we do machine learning like that? That's clearly worked really, really well in calculus. This should work in machine learning, too. So what Jeff was showing in class was the idea of just approximating a function like that as a piecewise constant function. And so on. I'm not going to draw all of it. Can people see why that's the next normal progression in this progression of ideas? What we get by going to piecewise constant function is we still get complete flexibility, but we still have a representation that we know how to understand. If we decide to represent our function with 1,000 pieces, then all we need is 1,000 parameters. If our function is f, we call the height here parameter f1, the height here parameter f2, and we would have a vector of 1,000 parameters, and we would have our completely general function. And this is where, if this worked, we would be done. We wouldn't need kernel methods. Unfortunately, this doesn't work at all. And this is the problem that kernel methods are going to solve. And do people remember or can guess why that approach doesn't work for machine learning? Overfitting. So why does it do overfitting?
Because my mistake, it can just, on the training data set, it can just adjust the function to correctly match that example, but fail elsewhere.
Exactly. So what he was saying is when you see an example, you adjust very, very locally, and you're not going to generalize. So if you think about how you would do a perceptron with a stepwise function in one dimension, is you would start with the function being 0 everywhere. You have to imagine that this is broken in lots of little pieces, all of which are 0, right? And you would try to optimize each of these pieces. And you would feed it your data set. So again, this is a 1D data set. You would feed points one at a time. So when you see the first point x1, you would represent that x1 in a way that is compatible as a feature with this representation. So you would say, you'd create a feature vector that says x1 is not here, x1 is not here, x1 is here. x1 is not here, not here, not here, not here. You would take this point. Is this clear why this is how you would represent a point for the perceptron? Is this not clear why you'd represent this point for perceptron? Oh, OK. Looks actually pretty clear. OK, so you would do this, and you would notice that this point is a 1 here, and you would look at its label, and if this was a plus, sorry, you would say, oh, let's make our function have a plus here. And then you would see, say, a minus here, and you would say, oh, great, let's make our function be negative here. And that's how you would learn it. But the reason this doesn't work, the reason this overfits, as somebody here very clever said, is you're really not getting a lot of information from this. If you saw a plus right here, you know intuitively that it's pretty likely that these are pluses too. Right now, they wouldn't be classified as pluses. They would be on the boundary, and you wouldn't know what to do with them. But that's because this representation did not incorporate the common sense knowledge that neighborhoods, that points are similar to each other, should vary similarly to each other. In some sense, maybe it didn't incorporate prior knowledge of how the world works, or it didn't incorporate smoothness assumptions. But whatever it is, that's the intuition, that you have a concept of neighborhood. And when you are updating something, you want to update the entire neighborhood, not just a little piece at a time. And this idea that you want local updates, because when you make a change, you don't want to change the entire function, but you want your updates to not be too local, is what leads to the concept of kernel methods. OK? So let's do this. Updates, they're local, but not too local. So what kernel methods do about this is they say, OK, let's define a concept of a neighborhood. The concept of neighborhood, or the concept of similarity, is defined through the use of kernels. So you define, sorry, let me put this one. So you define a function which is the k centered at some point xi, which is called the kernel function. And you use this function to quantify how similar other points are to xi. So when you write kernel of xi, kernel at xi of x, this is a number that tells you how similar xi and x are. Because this is the intuition, we tend to see kernel functions looking very much like blobs. And I'm very tempted to refer to them as blobs for the next of the term. The reason they do that is if this is xi, the center of the kernel function, you can see that a function like this captures the intuition that we're looking for here. If you're smack on top of xi, you're very similar to it. If you're kind of close to xi, the function returns a reasonably big value. And if you're over here, you're really, really not similar. That's why a lot of functions that are kernel functions look like this, like a Gaussian. You've seen other distributions too, and maybe they'll be, more peaked or less peaked or shaped whatever. But it's a good way to think about them as blobs. And what kernel methods do with this concept of a neighborhood with this kernel is that they say, OK, we shouldn't do these super local updates. Let's just update the entire neighborhood proportional to the similarity. So if we were still representing this in the way if we were still representing this function with a piecewise constant function, which you could in theory do just fine, you would imagine that the next time I want to do a modification, for example, here, I'm not just modifying this, I am slightly modifying these as well. This is what the kernel idea would do if we would be working on piecewise functions. Okay? Now, if we came up with idea, there's absolutely no reason to go back to piecewise functions because it's kind of a clunky representation anyway. How many pieces do you split them in? If you split them in tons of pieces, you have like a very big representation. This was an idea that was getting us to think in the right direction, but we no longer need it. Because what we're going to do with kernel functions now is to say that what we plan to learn, the function that we plan to learn that was going to be linear here and polynomial here and piecewise constant here, the function we're going to learn with kernel methods is going to be a sum of such blobs centered at the points where we see data, informative data, centered at the points where we see counterexamples. So the class of functions that kernel methods learn is the following. They learn functions that are created by, as I was saying, adding blobs at various points and with various magnitudes, and then taking the sum of all of these blobs to get a function that essentially looks like this. Not my best drawing. Is this clear? OK. So formally, mathematically, what this looks like is kernel functions are functions that can be written as a sum, a weighted sum of kernels centered at some points xi. This is it. I'll keep talking, but this is basically it. The idea of kernel methods is that you construct a function that looks like this, that is more general than linear functions and more general than polynomial functions. And why is it more general? To go, because it kind of looks a lot like, what you get looks a lot like polynomials. The reason this is more general is hidden subtly in this sum. this sum can be arbitrarily big. When we looked at polynomials, we said that we were going to look at polynomials of a certain degree, say degree n. This representation doesn't do that. We know that it's not infinite because if we see 20 data points, we can add at most 20 blobs to our function. So it's finite. But it grows with the size of the data set. So in that sense, it's flexible. It could be as big as you need it to be. And the idea is that if you were to see 1,000,000 data points, and your function was so bad that each of 1,000,000 of them were exceptions, you would get 1,000,000 blobs, and that would be a very, very complex function, much more complex than you would get with any other representation. Okay? Okay. So I want to just be clear that this is exactly what you guys have been implementing and asking me about what those alpha i's are. When you implemented the kernel perceptron, what you did was the following. You chose a kernel, a function, which was, what did I give you to do? A polynomial function, sorry. Yes, you choose a polynomial function as a kernel, and you started cycling through your points, and you started with f being completely 0, as represented by the fact that all the alphas are 0. And whenever you saw an exception that said your function should be bigger or smaller than it was, for example, if you labeled it as a minus and you saw a plus, aka your function should be bigger, you said, fine, I'm going to add a blob on top of this point to make it bigger. And you added a blob by incrementing alpha i. Specifically, you added yi to alpha i. You incremented when you need to make your function bigger, and you decremented when you need to make your function smaller. And then you returned the function, this function you computed, you returned it by returning the alphas, because you don't need to return the k's. This is something you can recompute each time. And whenever we asked you to evaluate this f somewhere, you said, fine. You plugged in the x here, you calculate the kernels, you sum them up, and you return the value. This is what the alpha i's are. Okay? Yes?
I get confused in the kernel. When do we normalize the input vectors? Because it seems like two identical small vectors can produce a smaller result than two very large different vectors. You say it's a measure of similarity, but like a lot of these times we do the dot product. And the dot product of two slightly askew vectors can be very, very large if the input vectors are large.
True. Let me think about that for a second, because I haven't thought of it that way.
Actually, I have another question about this. So
Go for
if
it.
we use this polynomial kernel, what is the difference between this kernel and the second polynomial?
So the first difference, and this is not actually quite your question, I'll be back to your question, but I know how to answer this one, so I'm going to answer it first. The first difference is that you could sum however many kernels you would want, however many of these like polynomial blobs set various parts of your data set, so your representation could grow as big as you wanted it to. The second answer is that there are ways in which they are similar. So if you take your kernel to be the first order polynomial, which is just a dot product, you know you've been told all the time that you're supposed to get back just the normal perceptron. Well, let's make sure that we understand how this happens. So if you take as your kernel this xi transpose x, this doesn't look at all like a blob. It looks like a line. And what this line says is, if I'm essentially like, it says the more similar I am to xi, the more I'm in the direction, the more convinced, like I can be as similar as I want to be. This can be infinitely big similarity, as opposed to here where it just peaks. And the more I'm in the opposite direction of xi, the more convinced I am that it's the wrong label. So here, when you have a blob-like thing, when you find something that's very different, you don't say, I'm pretty sure you have the wrong label. You just say, I have no idea what label you have. If you take something like this, you say, oh, if xi and x are pointing in opposite directions, so their product is small and negative, then I'm just going to tell you, look, you have the wrong label. You should swap the labels you have, okay? So, but sorry, getting back to your question was, they're not that different because indeed, if you put in a order 1 polynomial in, it's just as if you're doing a linear function, which is the simplest version of a polynomial. So they can be the same thing here, but with kernel methods, because you're adding 1 for each exception you have, each data point, your representation can grow as complex as it has to, okay? Okay, so back to your question, the normalization question. Honestly, I have to think about it a bit offline. Is it okay? Let's just talk at the end of the class, because I'm not seeing it on the spot, and I don't want to keep everybody waiting whilst I'm being silly. Okay. Unless Ab knows. Okay, then we'll think about it. Okay. So the takeaway from this part of the talk is that kernel methods are a method for learning an arbitrarily complex function that's built as a sum of blobs that has this type of formula. And it's useful for doing exactly what you're saying, which is coming up with more complex decision boundaries or coming up with more complex regression functions. Go for it.
One question.
Yeah.
In case that we use like a polynomial function as our kernel, we're still getting like a polynomial decision boundary, right? Because I mean, if we sum two polynomials.
It can. So that's definitely a good intuition in 1D.
Yeah.
In multiple dimensions, it gets a bit weird because if you think about it, like you're getting, if you're trying to come up with a decision boundary for a data set in 2D, the visualization of your function is a 3D function, right? And that 3D function, when it looks like this, if you look at the actual decision boundaries it creates, those can be hyperbolas, for example. So like there's a difference between your function is polynomial and your decision boundary is polynomial. Okay. Anything else? How are we doing on time? Okay, so I want to cover 2 more ideas, and I don't know if I'll have time for both of them, so I'm going to submit this to a vote. Who wants to hear more about that entire topic of think of functions as being part of a vector space of functions and how we use the vector space of functions to analyze the performance of the perceptron? That's the first. The second option is the entire idea that you can see kernel methods. So the way we've been seeing kernel methods is learning a function. We can see kernel methods as a feature projection to another, to a feature map that might be infinitely dimensional, and that's called the kernel trick. So one is talking about analysis of kernel methods, and the other is talking about what do we mean when we say kernels are projection to another space. Who's for one? Who's for the other? Okay, the other is a bit more. Sorry for the vector space people. Okay, so is this visible or is it blocked by that? Visiblish? Visiblish. Okay. So the slightly unsatisfactory part of the explanation that's going to come is that I can't show you all the proofs. There's going to be a key step where I'm going to have to say you guys have to believe me, because it's a whole book of it. But I'm going to try to give you the intuition here, okay? And the intuition is as follows. We have a concept of a dot product, of an inner product, right? We know what an inner product means for vectors. And we know in the just normal vector case that an inner product between two vectors is in some sense a measure of their angle. Because if you have a vector u and a vector v, the inner product as it's defined for these vectors is the norm of u, the norm of v, times the cos of the angle between u and v. So you can think of this inner product as measuring some form of similarity. It would be a better measure of similarity if we normalized it by u and v, by the way of your normalization questions. But to a first degree of approximation, it's a measure of similarity. If I say similarity quite this many times in a row, it should remind you that what we meant to do with kernels was also to measure similarity. So the first note, that the first thing that people observed is that you can build kernels by taking inner products. So they said, oh, okay, so the first trivial kernel is just the inner product between xi and xj, kernel set at I at x. And then they said, well, if we actually want to run this in practice on data, we could actually take any transform of the data first. So if we thought of any sort of feature transform, whatever it is, you don't have to think numbers here. Like, you know, the example of the feature transform people gave is from x to x squared, yes?
What's the difference between the inner product and the dot product?
The dot product is the term used for inner product when we're talking about vectors. Inner product is a more general term that can be used. For example, you could take the inner product of two emails if you so wished. So the inner product is the generalization of the dot product to arbitrary objects. And the way that generalization is done is so that it satisfies some basic axioms that are the axioms that we think are intuitive. So for example, with inner product for vectors like these, we know that it's symmetric. If you take the inner product between u and v, it's the same as the inner product between v and u. People who wanted to generalize the concept of similarity through inner products, through dot products, said, oh, okay, this seems like a useful property. So they set it as an axiom. So something that has this axiom plus a whole bunch of other axioms will be called an inner product. And they always capture this notion of similarity. So going back to this idea, we said, oh, kernels are like similarity too. Same idea. So one way to define a kernel is by taking an inner product. And that inner product doesn't have to be on the original data. It could be on any transform of the data. So if we defined a feature transform phi, and we took the inner product in this transform space, this would again just be a similarity in just a transform space. So this link between inner products can generate kernels was the first trivial thing. Now the fascinating result, which is the result I'm going to have you guys to have to believe me because it's not easy to translate, to prove, is that this holds in reverse. That whenever you have a kernel, as long as that kernel is a good enough measure of similarity, where good enough has a mathematical definition that I don't want to go into right now, but as long as you've defined your kernel in a way that captures similarity fine, then you are guaranteed that there will be some way of thinking about your data, there will be some transform phi, where the kernel that you started from can be written like this. And all that the intuition is behind here is that both inner products and kernels measure similarity, so you can imagine how you can map them to each other. Okay? Now, this perspective that you can start with a kernel, I give you a kernel, I give you a function, say it's a polynomial, and you know that theoretically there's a phi there, seems at first not helpful. Seems actually quite annoying, because you don't know what the phi is. You don't know how many dimensions it has. So if I give you something like a Gaussian kernel, you actually can't tell me that phi, what does it return? Is it finite or infinite dimensional? And you have no guarantee that this transform makes any sense. Like, not immediately, intuitively. You're like, OK, I give you a kernel. You tell me that a transform exists. So what? Well, there is clearly a good so what. Otherwise, not everybody would be talking about it. And that so what is that by casting an arbitrary kernel that might look like a blob as an inner product, which an inner product is linear in a more general sense than what you've seen before. Linearity in the general sense just means, you know, like if I take the inner product of alpha x plus beta y with some z, this is just as if I'm taking alpha xz plus beta yz. That's the concept of linearity in general. So the reason this idea is useful is because you've reduced your very complicated, weird, blobby-looking problem to something that, again, behaves in the same way a line behaves. The reason lines are very easy to deal with is that they do that kind of thing. They distribute sum and multiplication. Because they do that, all the formulas that you have to use them in work really easily. Their derivatives are very easy. You can invert them very easily. This idea of linearity as well behaved tells you that the theorem that we've been talking about takes something that you have no idea how to deal with, and at least abstractly, at least in your mind, even if you don't know what the phi is, tells you that you can treat it as if it's linear. OK, people are giving me weird looks. Any questions? Which part of it did I lose you at? Go for it.
I'm not sure why putting the phi's in the inner product makes it a linear problem.
So it's not the phi's that make it a linear problem. It's the fact that, let me erase this because it's not necessary. It's the fact that it's an inner product between two quantities. So the way to think about it is, you don't know what phi is, but phi exists. It's somebody. So in theory, all of this is in theory, when I give you an x1, you can go ahead and calculate phi of x1. This is now a quantity. It's not a function. It's not nothing complicated. I give you an x2. You calculate a quantity. And then you just take their dot product. And the key idea here to remember is that dot product between two things is something that is linear. That's the result that maybe is not obvious to people. Is that a confusing statement? Go for it.
Except for if you don't know what phi is like, if you have, so when you talk about linear and you have a constant times something, it's a constant times the inner product. The constant might not come out of the phi. Does that make sense? So like even though you're multiplying by constant, when you do the transform, you don't know what happened. That makes sense.
I think it made sense. You're saying you're finding it hard to imagine that phi of xi is just a constant, that you should think of it as a constant, not as a function. Because you don't know what this function is doing. If you multiply this by 2, maybe this function multiplies it by 4.
Yeah, so just because you have the kernel of like 2xi, does it mean it's to the kernel of xi, since you don't know what happened to the 2?
Right, so it's not linear. OK, oh, good. Thank you. It's not linear in xi. It's linear in phi of xi. Maybe that should answer both of your questions at once. So what it's saying is, I take my data set. I don't think about anything yet. I just am given a phi. And I use the phi to change my data set in potentially a much higher dimension space. And in this much higher dimension space, I measure similarity between 2 points through the inner product, which is essentially just like measuring similarity between 2 points in the non-kernelized version by taking their dot product. So let's try to write this down. So here's the pipeline. The pipeline is like this. Somebody comes and gives you a kernel. Says here, use K as the, I don't know, like RBF kernel. Okay? I'm handed a kernel. And I say, haha, even if I can't tell you exactly what phi is, I know that there exists a phi that is a transformation from my original points to some new points. And the moment I was given that kernel, intuitively in my mind, I take all of my points and I transform them. And I no longer care what the original points were. I now have a different set of transformed points. And you can think of those transformed points as constants. Okay? This phi that I am talking about has a very important property, such that it has the property that it has taken the concept of similarity I fed it, and it has transformed it so that if two things were similar according to the kernel, if x and y were similar according to the kernel, then the transform of x and the transform of y will be similar according to inner product. So it has the property that if xi and x are similar, then their transforms are similar according to taking the inner product. If I was, oh, it's not f, it's phi, sorry. If I was sure that this phi was finitely dimensional, and I don't even touch that with a 10-foot pole, but if I was sure, then I could just write phi of xi transpose phi of x. And this would finally look to people like a simple linear thing we know how to deal with. Is that true? Oh, I see more nods. We're getting somewhere. Wonderful. So, okay, here's what we did. We said, your boss hands you a kernel. You say, aha, I know there's such a phi. And I can think in my mind that I've transformed the data to this phi, such that the data now is characterized by linear similarity. That's maybe a way to think about it. Like just the normal distances we're used to in our normal spaces, like R2, capture what we're interested in the data in the general space. Okay? If you do this, what has this unlocked? What has this given us? Why is this crucial?
We don't need to compute a phi.
We project it into the phi space. So yeah, so you simplify our calculations, like you are doing random kitchen sinks for the RBF kernel, right?
So that again, both of you guys are giving me like 5 steps of reasoning ahead of what I'm looking for. All of them are true details, but I want to make sure that all of us understand what's going on here.
That in some phi world, we have a linear decision boundary?
Exactly. In the phi world, I love the word phi world. This is how I'm teaching from now on. Ta-da! So step 3, because of that, there is a phi world where it makes sense to look for a linear decision boundary. I'm not going to say there is one, because I'm not sure there is one. I cannot guarantee that they're linearly separable. But what I know is that the linear distance between them is representative. If you look back This example ages ago. The problem in this example that didn't let us have a linear decision boundary is that linear distance between points just didn't tell us anything, right? Like, we know that these are similar, we know that these are not similar, and yet these have the same labels and these don't. The key reason this thing failed to do linear separation is because linear distance didn't mean anything. But what this result tells us is that there is a phi world where linear distance is meaningful. And we know that linear distance is meaningful in that phi world because we calculated phi based on the kernel that our boss gave us that we said is meaningful. Like, the way to think about this is the following. Say that you're taking 2 emails, okay? You have no idea how to think of emails in terms of vectors in R to the n. But if somebody tells you that you know how to compute similarity between emails by, for example, doing TF-IDF and computing some score or another, or by intersecting their words, then somebody can compute a kernel that tells you how similar these 2 emails are. And from that kernel, we know that theoretically, we can project those emails into a space of numbers that might be infinitely dimensional, where emails that are similar are at similar distance, and emails that are dissimilar are not at similar distance. That is the power of this result. Because once we know that we have such a phi world, was that the word? Once we know we have such a phi world, we can go ahead and apply our trivial, linear, boring algorithms, the first step of today, into that phi world. So you can imagine that what I just said is the following. For any 2 objects, cats and dogs, if I can write a function that tells me how similar they are to each other versus how dissimilar they are to each other, and if I can make sure that that function has some basic properties that I wanted to have that are just, you know, the mathematical small script, then I can go ahead and write an algorithm that classifies my cats and my dogs using just the simple SVM. That's the power of it, okay? So now the last question of this is, okay, so you're telling me you're going to apply SVM into the phi world. How the hell are you going to do that if you don't know what phi is? And that's, you all, I think, already have an answer to this question. How do we do it? Exactly. Because if we're in a world where what we care about is distance, linear distance, we're going to compute that distance with dot products. And we know how to compute that dot product without using phi. So essentially, the 4th step here, if I have a phi world where linear distance is meaningful, just use linear classification algorithms. Where I compute the distance between 2 points through the nice formula that my boss gave me. And that's it. And this 2 perspectives of looking at the same problem, the perspective we did in the first half an hour, which was we're learning a function, that's the perspective that's intuitive for you to figure out what kind of kernel you want to choose. What kind of, you know, how is the decision boundary going to look like? All of these things, when you're trying to get intuition of how to apply kernel methods on your data set, you have to look at the first intuition. The kernel methods are learning a function. When you want to do a different task, which is to say, I want to be able to learn something really difficult using existing tools, then you think about the second perspective. You think about the fact that if you have a kernel function, you can take any linear algorithm and kernelize it through what is called the kernel trick. That's all that the kernel trick is. The kernel trick is this line over here, that whenever you have to compute a dot product, you compute a kernel instead. And the reason that these two perspectives are equivalent, we said, is unfortunately a leap of faith, which is this leap of faith. That whenever you have a kernel that represents similarity well, there exists a phi. There exists another space where that same concept of similarity is represented linearly. Okay? Yay. So how are we doing on time? Okay. So go for it.
This faith, is it actually proved, or is it something that people just believe?
Oh, it's proved. It's proved. I can tell you the book that builds up through the proof.
So it's not just a faith?
No, it's not. We were not doing faith here. Go for it.
How do you know that the kernel that you pick or that you're given is suitable for the data?
So the answer, there's a answer that pretends we know what we're doing and an answer that's honest. The answer that pretends we know what we're doing is you visualize your data, which clearly is going to work for emails, but you visualize your data, and you see what kind of idea of similarity makes sense. Let me give you a very simple example. If you have a data set where all the pluses are in a circle like this, and all the minuses are in a circle like this, and you visualize it and you see that that's what you're doing, how would you measure similarity between 2 points? Don't give me a fancy name, just give me the intuition. True, but that's not quite an answer to what would be your kernel function. Like, you're the boss, you have to give a kernel function to your underling. What MATLAB file do you give them?
Measure how far you are essentially.
Exactly. So for any 2 points, you take the radius to both of them and you subtract it. And if they have the same radius, they're similar, and if they have different radiuses, they're dissimilar. And you take the 1 over that difference so that you can get something that measures similarity, not distinction. So the first answer to how you choose your kernel is you look at your data. And your data should suggest something about how to choose a kernel. The second answer is that if your data is in 100,000 dimensions and you're not going to plot it, then there are a bunch of kernels that are known to work well. What does it mean they work well? Well, they're just so flexible that given enough training data, they will be able to give you such a complicated boundary that will definitely capture what you want. Now, why don't we go with these kernels in the first place? Because of the first part of the sentence I said, with enough data. Yes, by taking a huge combination of different bits with different weights, I can generate any function. But if I come up with something that's already that the bits are more representative in the first place, I won't need as much training data. So essentially, if you know anything about your data, coming up with a good kernel is useful because you'll be able to train it with less data. But if you don't know anything about your data, just throw it the standard kernels, try 3 or 4 of them, and see which one of them does best with the amount of data you have.
Yeah, can you explain more about why, when the linear distance is meaningful, then we can use linear model?
because that's a great question. So what I mean by a linear distance is meaningful is that things that are close to each other by our intuitive understanding of close to each other have the same label. And things that are far away from each other, something that's far away from this guy, I expect it to have a different label. There's nothing that tells me that this data set will be perfectly separable. There's nothing that tells me that there isn't a minus here. But if I told you that in general, I find it meaningful that things are similar to each other or far away from each other, it means that in general, the things that are pluses are clustered together and the things that are minuses are clustered together. And because they're clustered together, you intuitively visualize this as two different things that you can draw a line between. Because if they weren't two different things that you could draw a line between, if they were like this, there would be too many minuses and pluses that are close to each other for me to have said that that's a meaningful similarity. Does that make sense? So again, like it's not a guarantee, but I just said, look, this is something, it makes sense. So it makes sense that they'll be separatable by a line. Anything else?
I'm just curious in the middle of the example, why you're using f of dots, because we usually see f of f. Is there some specific reason why you're using f of dots?
No, I just like that notation. Go for it.
Sort of in the same vein, like when you're doing the kernels, if you do k sub like xi of x, that's the same as k of xi comma x, right?
Yes. The two notations are used interchangeably, but each of the notations suggests something different to think about. The way, whenever you have two perspectives of the same object, each of them tells you something a bit different. By using the notation x underscore xi of x, what I'm trying to remind you of is that those kernels, like that f, which will be a sum of those kernels, is a function of one variable, which is x. So that you don't get confused, is xi a variable, where is it coming from? Xi plays a different role from x here. Xi is a fixed center, and x is something that you just feed it. So because they play different roles, I like to keep them separate. In places where you're going to take the kernel between 2 points that behave as the same, like whenever you take the kernel between an xi and xj and they're both fixed, it's more intuitive to use the other notation because it's showing that it's symmetric. Anything else?
Can we apply kernel to multi-class problem?
I'm pretty sure we do. I have no idea how to do it. It's not my area of research. But I'm sure you can.
And is there any proof that there always exists a phi space that can linearly separate any data set?
So the proof doesn't say that there's always a phi that linearly separates. What the proof says is that there's always a phi such that that kernel can be written as a dot product of phis. So that wasn't perfectly clear. Let me get this. So again, the proof says this. If I give you a kernel, there is a phi such that this equality holds. Okay? That's the only thing that the proof says. It doesn't say that if I feed you a particular data set, it will be linearly separable by phi. It just says the notion of distance in the original space as measured by the kernel is the same as the notion of distance in the transformed space as measured by linear distance. So if your data set was separable according to that notion of similarity, for whatever that means, that it was separable according to a notion of similarity. Like if your data set in the original space clustered where things that you said were similar had the same label, and things you said were dissimilar have different labels, then what this theory guarantees is that in the transform space, things will cluster, things that are similar on one, things that have the same label on one side, and things that have a different label on the other side. But if they didn't cluster in the original space, they're not going to cluster in the transform space either. Okay?
Right. Yeah, but my idea is that if we can prove that there exists a phi space that can perfectly linearly separate two data sets, then our goal is just to find this perfect phi.
Gotcha. That is a very interesting research problem. I've not thought of it that way, and I don't know of anybody who has already. So, yay. Okay. Thank you for a very thoughtful question. Anything else? So according to my time, it's 6. I'm willing to close it here, or I'm willing to spend another half an hour talking about the third point, which is what's the entire topic with vector spaces. If, by show of hands, and I won't be judgmental, you can all close your eyes, who would be interested in staying for another half an hour? Okay, so anybody who's tired, like let's take a 3-minute break. Who wants to leave can leave, and then we'll talk about the third topic. Okay, so let's recap what we just saw, because we saw a lot of things. We saw that there's a way to think about kernel methods as doing 2 things. One of them is that they're learning a wiggly function like this as a sum of blobs set at certain points. And the other one was that it takes your data set and it projects it to some crazy ass space where linear distance means what it should mean. So we can do linear classification. Okay? Those were the 2 meanings. I'm going to represent the second meaning as saying, using this example we saw in class, where if you have this data set that's not linearly separable, you can project it to a space where it is linearly separable, which is something like this. And now you can linearly separate it. This is perspective 1, this is perspective 2. Okay. Both of these are nice and fine perspectives, but none of them has yet told us that an algorithm based on learning such a function, like this one, or making such a transform like this one, actually works. Intuitively, we've argued everything intuitively until now. Surely, if we're like putting blobs, that's helpful, etc., but we've never proven anything. And the last part of this class is to give you the tools to think about proving stuff. And the way we're going to find these tools is to look at how we prove stuff when we say in our normal space, R to the n. Okay? So what we're going to do is we're going to go back to the sadly overdone proof of the normal perceptron and look at what we did there. So, normal perceptron versus kernel perceptron. I'm going to rephrase the proof a bit differently than you saw it in class. And I hugely recommend you go back through the class notes and see that the 2 ways make sense together. Because what I'm trying to do here is to give you more insight into how the proof in class was, how people came up with it. Like we saw in class that it works, but that doesn't mean you would know how to rederive it. So the proof of the perceptron in class started from a very simple idea. You know that there is some optimal decision boundary, we're going to call it W prime, that linearly separates your data set. I'm going to go through the proof for the perfectly linearly separable data set. You can imagine that there are ways to modify all of this to go for the non-linearable data set. Well, let's go through a simple example to get intuitions, okay? So if you have a linearly separable data set, you know that there is an optimal decision boundary, and you're going to express that decision boundary through a W star. Now, if you have an algorithm that it iteratively adjusts a W, so creates a W1, W2, WT, and you want to figure out if this algorithm converges, what you want to do is to somehow measure how close your WT is from the W star. So if you imagine, if this is the optimal W star, and after you've run your algorithm for a while, you return a decision boundary that's like totally different, a WT, then you wouldn't count this as your algorithm working. The difference between the angle of these lines is too big. And in particular, or another way of looking at it, the difference between W and WT is too big. But if you had a circumstance in which this was the optimal W star, and you learn something like this that has a very similar W, these W and W stars are very similar, then you would say your algorithm is doing a good job learning. And especially if you can show that W and W star get closer and closer to each other, then your algorithm converges to the ground truth. That's the basic idea. Go for it.
In this case, W star is just any W that will separate your two cases, or it's optimal in the SVM case of, margins, because you could have multiple.
Gotcha. That's a subtle point. Thanks for raising that. The way to think about it is that your data, you're seeing a small sample from an infinite distribution over data. And when you say that you assume that this data is linearly separable, the way I'm not even sure that's the right way to think about it, but the way I think about it is that I saw a sample from lots and lots and lots and lots of data points, and they were all exactly snug, and there was exactly one separation boundary. You never know, because you never see all of the data points, what that one true separation boundary is. The perceptron has, and not just the perceptrons, SVM as well, have a lot of leeway around that true separation boundary. The perceptron is fine returning any of them. The SVM attempts to say, oh, I know what the right one would look like. It's the one that has a lot of buffer, and returns that one. But you can think that there's an underlying true W star. OK? Go for it.
So just to paraphrase what you said, so since we're only doing the perceptron right now, W star is not unique. W star is anything that has the optimal misclassification error.
No. Well, you did paraphrase it, but that's actually not what I meant. So what I meant, and sorry that I didn't get that clear, is there is a true unique W star. The perceptron, you can think of the data, the infinite data, as covering the entire plane, the entire R2 plane, and the plus points and the minus points being snug against each other on a precise linear boundary. That's W star. Because you see lots of because you see only a few data points here and there, you don't get this snug boundary. So for a finite data set, any bunch of W's would work.
Right, that's what I'm saying. So for it seems like, at least that what it sounds like to me is that for a finite data set, W star is not unique, because you could get the correct result with a number of different vectors, because there is that leeway.
True. But what I'm doing here is saying I assume that my finite data set is drawn from a distribution.
Oh, okay.
And that distribution has an existing W star, and that W star I'll never know. It's an abstract W star just like phi, but it exists.
You get it as a sample.
Yes, exactly. Yeah, exactly. So going back to the original point, what I want to do in the perceptron is I want to see if my perceptron converges by seeing if the W I'm computing gets close to an abstract W star. Okay? And I will measure the similarity by looking at similarity between two vectors, the one I computed and the ideal one. And how do we know how to measure similarity between two vectors? Inner product, exactly. And we actually said that the inner product is not a perfect way of measuring similarity because it doesn't do normalization. So in reality, how we're going to measure similarity here is the normalized inner product. So we're going to measure similarity by taking the dot product between our current one and the true one. And we're going to divide it by the norm of the true one times the norm of this. And we proved a few whiteboards, blackboards ago that this is just the cos of the angle. Okay? This should start looking similar to the proof in class. Because, think about this. If this ratio is a cos of an angle, this ratio is between +1 and -1, right? Okay, good. So in particular, this ratio is smaller than equal to -1. Sorry, smaller than equal to +1. So if our ratio is very close to +1, our cos is 1, so our angle is 0, so our two vectors are on top of each other. So what learning means to us is this ratio is as close as possible to +1. That's what learning means. And what we did in class is we did a small transform of that. We said if the ratio is close to 1, it's as if saying the top of this minus the bottom of this is close to 0. Do people see that? You just multiply and then subtract. So that's what we did in class. We said that the top minus the bottom is always smaller than equal to 0, because this is always smaller than equal to -1. To +1, and the difference between these two terms is a measure of how good I'm doing. And the closer I am to 0, the better I'm doing. So in the perceptron proof, we computed this term, and we computed this term, and we wrote that this minus this is smaller than equal to 0, and we got a convergence bound. Do people remember this? Good. What I want you to notice here is that we needed two concepts to achieve such a result. The two concepts were the concept of an inner product and the concept of a size of a vector, so we can normalize that inner product. The inner product is something that means similarity, but is also linear. Those are the two characteristics of a nice inner product. So that's what we want. And because we ask linearity, it doesn't do very well with sizes, so we normalize it. So we need a norm as well. If these are the two concepts we needed for proofs in R to the n, then in order to generalize these proofs from R to the n to functions, we're going to need to generalize these two concepts. And that's why people introduce the concept of a vector space of functions. The goal of that concept is to give you the tools to do such type of analyses. Okay? So what is a vector space of functions? In general, a space, I saw that the question was asked on Piazza, what is a space? A space is a mathematical technical term for a set of things, for example, functions, that I told you have certain properties. If it's a vector space, I told you that it has the properties that you can add them and you can scale them. If it's a vector space that has an inner product, well, I just told you that. It's a vector space and has an inner product. If it's a vector space that has an inner product and a norm, those are the properties. So when I say that I'm going to look at my functions and consider them as part of a vector space of functions with an inner product and a norm, that's all that I'm saying, that these operations and these quantities will be defined. Okay? So we said that to run the kernel perceptron proof, what we need is a concept of inner product between functions, some f that I'm calculating, and some f star. This inner product will capture some notion that my functions are close to each other. Just the way the inner product between two vectors captured the notion that the vectors are close to each other, the inner product between functions will capture the notion that they're close to each other as functions. which is what I'm looking for when I'm doing convergence. And then I'll also define the concept of a norm of a function, which for vectors we saw that the intuition is that the bigger the norm in our perceptron case, the more we felt like we're, remember from perceptron that big norm was equivalent to small boundary? Think of the intuition there as big norm is something complex. It wasn't a clear, simple model with lots of space. It was a complicated model that might overfit. It will be the same concept here. Again, I don't want to go into super much mathematical detail because there are a lot of proofs, but I want you guys to remember these concepts, okay? So we have these two things that we need to define. How are we going to go about defining them? The way we're going to go about defining them is starting from this guy first, from the intuition that an inner product should capture a similarity. So we know that our functions f, if they've been generated as kernels, what formula do they have? What types of functions am I trying to define these two things on? Yep. Yeah. So there are some sums of phi kxi of something. So I'm trying to define similarity between these two things. Well, if I'm trying to define similarity between these two things, it seems intuitive, say if it's not intuitive, that I first need to define similarity between these two guys, what it means for the kernels themselves to be similar. Because if I'm building my whole function from like sums of kernels, if I can compare kernels, I can compare functions. True? Okay, so our job is to define now what an inner product between a kernel of xi and a kernel of xj would be. That's our job. In other words, our job is to put a number to the concept of how similar is this blob to this blob. What proposal do people have? Especially considering that I want to compare these two blobs and I want to get a reasonable number, and I want to compare these two blobs and I want to say, oh, those are similar. I want to get a higher number.
Get the center x at the center point of this blob, which is like xi and xj.
So take the centers, which are xi and xj, and do what with them?
Yeah, like compare the similarity between the center.
Exactly. And how do I compare the similarity between the centers?
To the inner product.
Say again?
Inner product. Between the, or the, like measure the distance between the.
Right. So you're making such a great, wonderful point. You're like feeding into all the points I wanted made. So one second. So let's recap what you just said, because it's going in the right direction. You have two blobs. You want to measure how similar they are to each other. A great idea is to measure how similar their centers are to each other. One idea of measuring similarity between centers is the dot product. But why did we invent kernels in the first place?
Linear distance doesn't make a lot of sense in the initial space.
Exactly, because the dot product is not helpful. So the idea of measuring the similarity between blobs, the similarity between their centers is right. But how should we measure similarity between centers? True, but not helpful here, because we don't have phi. Yes, by the kernel. That's why we define kernels. We define kernels to tell us when they're similar.
Look at the distance.
Calculate a k of xi and xj.
Exactly. So we're saying that the similarity between the blobs represented by the kernel is just the kernel calculated at the two blobs. This like makes your head bend a bit. But if you go through it really slowly, it makes sense. I promise. So think of it this way. Let's recap what we did. We have functions that are sums of blobs. We want to be able to tell if our function converges to a ground truth function. To tell if the function converges to a ground truth function, we want to define an inner product between functions which captures some notion of similarity. We then looked at our function and said they're all sums of blobs. So if they're sums of blobs, I want to be able to compare two blobs to define a similarity between two blobs. These blobs are still functions. They just look like that. So I'm still trying to define a similarity between functions, just some particular simple types of functions. What's up?
I just want to make sure you know there's a class here at 6:30.
Yes.
You're running a little late. Keep your time.
Whoops. Okay, 2 minutes, is that okay?
No problem. I just want to make sure you do.
Yes, thank you. I didn't know what time it was. Thank you so much. Okay, we're going to do this really quickly. God damn it. I'm sorry, guys. Okay. To finish the explanation really quickly, we said the following. To compare functions, if the functions are made of blobs, we compare blobs. To compare blobs, it makes sense to compare their centers. To compare their centers, don't compare them linearly, because that's why we left linearity in the first place. Compare them with the kernel itself. Okay? So we define an inner product. I'm going to leave it to your imagination, because we have to go. How from the inner product of the pieces, we put the inner product of the thing together. And I'm going to stop because I really have to go. But the summary of the point of this was, if you want to deal with convergence, you're going to need to come up with these technical ideas. The technical idea of dot product and the technical idea of norm. It makes sense how to define them. And once you've defined them, and you can look back at notes, I only had time to go through a third of it, but once you've defined them, you can run proofs on them just the way you ran before. Wherever you had a dot product between points, you now have a dot product between functions. Whenever you had the norm of a point, you now have the norm of a function. So by this idea of generalizing these concepts from points to functions, you can now run the proofs exactly identical. That's it. Thank you, guys. You're wonderful.
Thank you.